Please note right at the outset that this broadcast is an AI-generated analysis. Welcome to our detailed technical review. Imagine you deploy a predictive model, right? And it gets like 99% accuracy on your local machine, but then the moment it faces real-world data, it just fails catastrophically.
Oh yeah, costing your organization valuable resources, time, everything.
Exactly. And why does that happen? It happens because building predictive models isn't just, a rigid collection of mathematical rules. It's fundamentally an art.
Right, which is exactly why today we're doing a comprehensive analysis of Norman Matloff's book, The Art of Machine Learning, a hands-on guide to machine learning with R.
Yeah, and our mission for this broadcast is to really go chapter by chapter through the core technical material. We want to show that intuition and your strategic choices matter just as much as the algorithms themselves.
We'll be focusing strictly on the underlying mechanisms of the models. So we're going to translate that advanced math into clear concepts for you, especially if you manage or build technical projects.
And a key concept we have to introduce immediately is the KeyMLR package. Matloff uses this all throughout the text. The letters stand for quick and easy.
Yeah, it's essentially a set of simple wrapper functions around complex algorithms. It lets you focus purely on the methodology rather than, tearing your hair out over software syntax.
Which I love. Think of typical machine learning software books as these rigid culinary cookbooks. They give you a list of ingredients, tell you exactly what to type in.
But they don't actually teach you how to taste the food or adjust the seasoning if something's off.
Exactly. This text takes the complete opposite approach. It aims to make you an informed consumer so you understand exactly why a model works, not just how to run a script.
Right. So to build on that foundation, we really need to establish the absolute baseline goal of all machine learning, which is simply predicting outcomes based on the principle of similarity.
The core of that is the regression function, right?
Yeah, exactly. When statisticians talk about the regression function, they just mean estimating the average or the mean of an outcome given a specific set of features.
Like estimating the average weight of people given a specific height.
Yep, that's the classic example. And almost all machine learning methods are basically trying to estimate that exact function. Matloff introduces this through the k-nearest neighbors method.
KNN.
Right, KNN. He uses a data set predicting bicycle ridership based on weather conditions, and the algorithm just operates on pure historical similarity. So if you want to predict how many people will ride bikes tomorrow...
It just looks back at past days with similar temperature and humidity and averages those ridership numbers together.
Spot on.
So transitioning from predicting continuous numbers like ridership to predicting specific categories is kind of the logical next step.
Right, classification applications.
Yeah, like predicting customer churn for a telecom company or diagnosing of vertebral disease from medical scans. But the underlying methodology is fundamentally the same, isn't it?
It is. The text really emphasizes that classification is literally just a special case of regression. You do it by converting categorical outcomes into numeric dummy variables.
Okay, so a customer who leaves the company becomes the number one, and a customer who stays becomes a zero.
Exactly. And then you predict the probability of that 1 or 0 occurring. But, and this is a big... But before you run these models, you have to be extremely wary of data preparation pitfalls.
Oh, absolutely. The book talks about the dangers of long-term time trends skewing data, or dirty data entries.
And missing data. For missing data, it discusses listwise deletion, which is just dropping the entire row if a single value is missing.
Which can be risky, but I think we really need to highlight a very specific pitfall. Unbalanced data.
Oh, unbalanced data is huge. It's so common for analysts to see a data set where, say, 95% of the records belong to one class and only 5% belong to the target class you actually care about.
And the book explicitly warns against the usual industry advice here, right?
Yeah.
A lot of people say you should artificially equalize the classes by throwing away massive amounts of data from the majority class.
Yeah, do not do that. The expert advice here is that discarding perfectly good data inherently weakens your analysis. You lose so much valuable context about the broader population.
So what's the recommended approach instead?
You preserve all your data and just simply adjust the probability thresholds for your final decision-making. Like if you're trying to predict which patients will no-show for a medical appointment, you don't throw away the records of the thousands of people who actually showed up.
Right, you just lower your action threshold. You might set the system to flag any patient with even a, say, 25% risk of a no-show for a reminder call.
Exactly. You adjust your actions, not the data.
Wait, if we go back to data preparation for a second, I really have to question the mechanics of converting every single category into a dummy variable.
Okay, what do you mean?
Well, if a data set has a feature like city, and you have 1,000 different cities represented, converting every single city into a separate binary column of ones and zeros is going to make the data set explode in size.
Oh, I see where you're going.
Right. Doesn't this risk creating just an overwhelming number of features, which leads directly to computational bloat and accuracy loss?
That concern is actually the perfect bridge to the most central problem in the entire field of machine learning, the bias variance trade-off.
Ah, there it is.
Yeah. Balancing model complexity so you avoid memorizing meaningless noise is the ultimate task of the analyst. Overfitting, which is high variance, and underfitting, which is high bias, relate directly to two mathematical variables.
Data set size, which is Noggler's, and the number of features, which is Dedaller's.
Exactly. So if you introduce thousands of dummy variables for cities, you increase your feature count, your field, dramatically. When field gets way too large relative to null of rent, the model has too much flexibility.
It just memorizes the random noise in the training data rather than learning the actual underlying pattern.
Right, which leads straight to overfitting.
I find that applying an analogy to an election poll really clarifies this trade-off.
Oh, let's hear it.
So if you're predicting a national election and you survey only 3 people in one specific rural town, your dataset size, your dollar-alls, is far too small. This gives you high variance.
Because the result is too sensitive to local noise.
Exactly. If 2 of those 3 people happen to belong to the same political party, your model assumes the entire country shares that exact view.
Which is obviously wrong.
Right.
Mm-hmm.
But conversely, if you survey the entire country with only one incredibly vague question about, like, whether they like the current economy, your feature set, P small, this yields high bias.
Because it's completely inflexible. It ignores all the critical local nuances that actually decide an election.
Exactly. It's too simple.
So to manage this delicate balance and stop analysts from accidentally optimizing for noise, the text advocates for rigorous validation techniques.
Like k-fold cross-validation.
Yeah, that's the standard approach. You partition your data into multiple distinct subsets or slices. The model trains on several slices, then tests itself on the remaining slice.
And it rotates that process iteratively until every slice has been used for testing.
Right, to ensure the accuracy metric is robust. But then there's triple cross-validation, which introduces a third, completely separate validation set.
So the final test data remains entirely unseen by the model until the very end of the tuning process to prevent basically cheating or p-hacking.
Exactly. But when feature bloat unavoidably happens, like your city example, you have to combat the curse of dimensionality using dimension reduction techniques.
Principal components analysis, or PCA, being the primary one discussed.
Yeah, PCA creates new variables that are basically linear combinations of the original features. It consolidates the predictive power into fewer columns.
The book also mentions some alternative modern methods too, right?
Yes, like feature ordering by conditional independence, or FOCI, and uniform manifold approximation and projection, known as EMP.
You know, understanding PCA can be really challenging mathematically, but it helps to visualize it physically.
Oh, I like visual analogies. How do you picture it?
Imagine looking at a 3-dimensional scatter plot of data points suspended in a glass box. If you walk around the box and physically rotate it, you'll eventually find a specific angle where the data is most widely spread out and visible.
Okay, yeah.
That is essentially what PCA does mathematically. It finds the optimal mathematical angle to view your data, allowing you to flatten or drop the less important dimensions without losing the overall shape of the information.
That's a great way to think about it. Now, having established how to manage features and validate predictions, we really need to address the limitations of neighborhood models.
Because k-nearest neighbors requires calculating the distance to every single historical data point, which is incredibly slow with massive data sets.
Yeah, it just doesn't scale. We need a faster, more systematic way to partition data. Which brings us to tree-based methods. Decision trees use flowchart-like binary splits instead of distance calculations.
The book uses the New York City taxi dataset and a forest cover dataset to show this, right?
It does. The algorithm basically looks at the data and asks sequential yes or no questions. It continuously splits the records into branches until it reaches a homogeneous group, which we call a leaf node.
But single decision trees are inherently unstable, right?
Yeah.
And prone to high variance. Like a tiny change in the training data can result in a completely different flowchart.
Oh, absolutely.
Yeah.
That's why you have to tweak the trees through ensemble methods. Bagging, specifically utilizing random forests, solves this by generating multiple independent trees.
It resamples the data and limits the features available to each tree so they grow differently, and then they all take a democratic vote on the final outcome.
Exactly. And then there's boosting, which uses algorithms like AdaBoost and gradient boosting. This takes a sequential rather than an independent approach.
So it repeatedly builds a single shallow tree where each new iteration specifically focuses on correcting the errors made by the previous one,
Right. And a critical concept to manage in boosting is the learning rate.
which dictates how aggressively the model adjusts to those past errors.
Exactly. Slower, more cautious adjustments achieved by setting a lower learning rate can effectively prevent the model from overcompensating and overfitting the noise.
And finding the exact right combination of all these settings requires grid searching for hyperparameters, right? Using that KFT function.
Yeah, because these parameters interact with one another so deeply, they have to be optimized as a combined set.
You know, the book mentions a famous quote by the creator of Random Forests, Leo Bryman. He famously claimed that it's impossible to overfit a random forest.
Yes, that quote.
I really have to challenge that assertion. I mean, is it genuinely impossible for a random forest model to overfit a data set like that quote implies?
Well, that quote is actually the source of frequent misinterpretation in the data science community.
Mhm.
What Bryman demonstrated mathematically is that simply adding more trees to the ensemble doesn't cause overfitting.
Okay, so the voting mechanism itself stays stable, whether you have 500 trees or 5,000.
Exactly. However, the structural parameters of the individual trees making up that forest absolutely still can overfit.
So if you set the minimum number of data points required to split a leaf node down to 1, or if you include too many features in the splitting process, your individual trees just get way too deep.
Precisely. They'll memorize the exact noise in the training data, and consequently, the overall forest will still overfit the problem.
Got it. Okay, so moving away from algorithms that draw these boxy flowchart-based boundaries, we transition to algorithms defined by continuous mathematical lines and equations.
Right, the mathematical shift toward parametric models.
Because many relationships in nature are smooth and continuous, which the classical linear model handles perfectly. It estimates outcomes by just drawing a straight line through the data.
Like estimating a professional baseball player's weight directly from their height.
Exactly. And for categorical outcomes, this takes the form of the logistic model, which applies that S-shaped curve to calculate the exact probability of an event occurring.
And the mechanics underlying these linear models involve a process called ordinary least squares. Every time you draw a predictive line through a scatter plot, there's a physical distance between your line and the actual data points.
Those distances are the residuals, right?
Yes. The algorithm mathematically adjusts the slope and position of the line to minimize the sum of those residuals.
And to evaluate whether this line is truly valid, the text really emphasizes using the adjusted R-squared metric over the standard R-squared metric.
Because the adjusted formula mathematically penalizes you for including unnecessary variables. It gives you a much more honest assessment of the model's true predictive power.
And when a linear model does incorporate too many features and becomes too complex, we use regularization.
Right. Techniques like ridge regression and the lasso, they intentionally shrink the classical coefficients calculated by ordinary least squares.
So deliberately shrinking the overall size of the coefficient vector reduces the model's flexibility, which helps control the bias variance trade-off.
Exactly.
I feel like the application of regularization, especially lasso, functions a lot like a gardener aggressively pruning an overgrown bush.
Okay, I like that.
Your complex model is the tangled, messy plant. By applying lasso, the algorithm acts as the pruning shears. It aggressively cuts away the external branches by shrinking the coefficients of less important variables entirely to zero.
Which forces it to drop the noise and rely only on the most robust structural features underneath. It's a great analogy.
But what happens when the data forms a shape that absolutely cannot be separated by a simple straight line or a flat plane?
That leads us to support vector machines, or SVMs. They utilize hyperplanes to draw mathematical boundaries between different classes.
And they use soft margins, right? Meaning they allow a few anomalous data points to cross the boundary.
Yeah, which prevents the boundary from contorting wildly just to accommodate a single outlier. But crucially, when data is really tangled together, the text introduces the kernel trick.
The kernel trick. Conceptually, that projects the data points into a higher mathematical dimension, right? It inflates the space until a straight, flat boundary can actually separate the categories.
Exactly. Now, while SVMs are highly effective boundary models, the text then introduces neural networks, describing them basically as linear models on steroids.
Because the architecture consists of multiple hidden layers of linear combinations stacked on top of each other.
Right. And these mathematical combinations are processed sequentially through activation functions. The book focuses heavily on the rectified linear unit, commonly known as ReLU.
How does ReLU work, simply put?
It acts as a simple gateway. It evaluates a number, and if the number is negative, it converts it to 0. If the number is positive, it passes it through unchanged.
That seems incredibly simple.
It is. But this simple mechanism introduces necessary nonlinearity, allowing the network to mold to really complex shapes.
And regularization within these networks is often achieved through dropout, where it temporarily deactivates random nodes during the training phase.
Exactly. That forces the remaining nodes to learn more robust, independent patterns, rather than relying on a single dominant pathway.
But the software reality of implementing neural networks in R is pretty complex.
Oh, it's a headache. Packages like Keras and TensorFlow operate as bilingual wrappers. You write code in R, which translates to Python infrastructure, which ultimately executes in highly optimized C code.
Wow. So that multi-layer translation can cause issues.
Definitely. It can occasionally cause convergence issues and random seed inconsistencies, meaning identical code might actually produce slightly different mathematical results on repeated runs.
That's frustrating. But, I must bring up a practical contradiction here. The text explicitly advises caution when applying neural networks to standard tabular data frames.
Yeah, it does.
If neural networks are so incredibly powerful and can mold to any shape, why does the book suggest avoiding them for, standard spreadsheet data?
Well, while neural networks can mathematically handle tabular data, their architecture is inherently designed to extract hidden hierarchical features from massive amounts of unstructured information. They excel at finding relationships that aren't explicitly defined.
Ah. And tabular data, by contrast, already consists of predefined, discrete features engineered by a human analyst.
Exactly. Applying a deep learning model to this type of data is often just unnecessary and inefficient. In the vast majority of cases, a well-tuned gradient boosting model or a random forest will completely outperform a neural network on standard tabular data.
And achieve higher accuracy with a fraction of the computational overhead. That distinction makes a lot of sense. So we can now look at applying neural networks to the unstructured data sets they were actually built for.
Right, like image classification using convolutional neural networks, or CNNs. The book utilizes the well-known fashion MNIST dataset for this.
CNNs don't look at an image all at once, do they?
No, they exploit spatial locality using a mechanism called the convolution operation. Imagine sliding a small magnifying glass step by step across an image. Okay.
The algorithm processes these small tiles of pixels, feeding the result into a pooling layer. Pooling summarizes that small window, reducing the overall size of the data while preserving the most dominant feature, like a sharp edge or a curve.
So this step-by-step process results in shape evolution across the hidden layers, slowly building up from simple lines to complex objects like a shoe or a shirt.
Exactly. Furthermore, the text details how to handle other forms of unstructured information, such as time series and text data, using much simpler machine learning methods.
Because for time series prediction, the primary challenge is that the data is sequential.
Right. So the book outlines converting this sequence into a rectangular format using a mathematical lag operation.
Meaning, by creating columns that represent the value at previous time steps, you transform time into standard features, allowing conventional algorithms like random forests to process the data efficiently.
Spot on. And for text data, the book utilizes the bag of words model, where it strips out linguistically insignificant stop words, like the or and then counts the frequencies of the remaining distinct words across the documents.
Yeah, and this process successfully converts raw paragraphs of unstructured text into a massive numerical matrix that standard classification algorithms can easily evaluate.
But, when considering the architecture of convolutional neural networks and text matrices, an enormous mathematical paradox arises.
Oh, regarding overfitting.
Yes. Classical statistical theory, as we discussed with the bias variance trade-off, insists that having more features than data points guarantees catastrophic overfitting.
Right, the pass it greater than 9 problem.
Exactly. Yet modern convolutional neural networks regularly possess millions of parameters. often far exceeding the number of actual images in their training sets. How do these networks function without just memorizing pure noise?
It's a great question. The text addresses this by linking back to the mathematical nature of overparameterization in polynomial regression.
Okay, how does that work?
Well, while classical linear models fail completely when p exceeds $7, deep neural networks operate under entirely different mathematical dynamics. The massive parameter space, combined with the regularizing effects of dropout and pooling, allows the model to find a configuration that perfectly interpolates the training data.
So because there are millions of parameters available, the network can create an incredibly smooth mathematical transition between the data points, rather than those erratic jumping boundaries we see in overfitted classical models.
Exactly. This smoothness allows the highly overparameterized network to generalize surprisingly well to new, unseen data.
Wow. We have covered a tremendous amount of highly technical ground today. Friends of the show, we strongly recommend that you read the actual book, The Art of Machine Learning, to truly grasp the practical R code implementations and execute these methodologies yourself.
Yes, highly recommended.
We encourage you to subscribe to our broadcast, and we politely wish you a great day. But before we go, we want to leave you with a final philosophical question extending the book's premise.
A little something to think about.
If machine learning is currently an art form that requires human intuition to carefully balance bias and variance, will the eventual perfection of automated hyperparameter tuning turn it back into a rigid mathematical science, ultimately making the human analyst completely obsolete?